For the steady state solution, it looks like this. So now from this solution, what it means is that the atoms are displaced by the light, right? So remember here, this is the position of the atom, or more precisely, it's the position of these electrons. So for these electrons, the displacement of the electron will also introduce a dipole moment because the electrons are charged. So this means that we actually calculate the how the dipole moment behaves as a function of time. Now, of course, it's a complex number, so only the real part means the dipole moment, and the imaginary part of that dipole moment simply indicates like what's the phase that is lagging by these atoms. So if you still remember from way earlier when we discussed the electrostatic fields in matter, so the polarization vector is simply the integration of it is simply the dipole moment per unit volume, right? So from the little p, we can get the capital P, which is the polarization vector. Now, from the polarization vector, because for weak electric field, the polarization vector must be linearly proportional to the external E field. So this means that this proportionality factor is the dielectric constant. So from the capital P and divide by the electric field, we get this part as the dielectric constant. Now, from the dielectric constant, we can also get the complex wave number, and also from the wave number, then we get the index of refraction. So in the end, we can plot that for a typical material, the index of refraction could look like a function like this. So here, this is the resonance frequency, so which means the frequency of the internal states. And so you see that as you go near this resonance frequency, there is a huge jump of this index of refraction curve. And here I didn't mention the alpha, but the alpha is so the alpha term indicates how much energy is being absorbed by the matters. So imagine that we having some material that's having internal energy levels that's exactly at omega j, and your incoming light is also at omega j. Then at this time, at this frequency, the matter will absorb the incoming light, and it will make spontaneous emissions. So which means that these light can be absorbed by the atoms, which results in some loss. So the alpha, you can think of that as a amount of absorption by the material. So near this resonance frequency, the absorption is huge. But it also indicates a strong change of the index of refraction. So when it's very close to the resonance, this part is called abnormal dispersion, because here, when it's very far away from the resonance, there is actually a very nice equation that characterizes the shape of this diffraction index of refraction shape. So if you do some approximation at the place where it's far away from the resonance, you can actually get a very simple equation called Cauchy's formula that can characterize this shape. So there are only two unknowns that can fit to this shape very well. So this is called the index of the coefficient of the refraction, and B is called coefficient of dispersion. So the larger the B, then the stronger this curving shape which will be. So this type of dispersion relationship is very typical for a lot of materials that is transparent to light. So, but we can still engineer the dispersion relationship, and which can produce very exotic light properties. I might be able to touch upon this later if we can finish it very quickly today. So okay, so then this summarizes chapter 9. So in chapter 9, we've already discussed how the waves behave in vacuum, and we also discussed how the wave behave in different media, and then how lights are refracted and refracted, and we also discussed how the lights behave in conductors, and now we also have a very brief picture of how this index of fraction could depend on the frequencies. So the next topic I want to discuss is actually from chapter 11. So so I skipped one subsection on chapter 9, which is the electromagnetic wave in guided in waveguides. But so basically, in waveguides, you have a confinement of the electromagnetic wave in x and y directions, and then so only the wave can propagate in the d direction, but the confinement in x and y directions actually provide you extra constraint on how waves can propagate along the d direction. So if you are interested, or if you are doing if you are thinking of doing some research related to say fiber physics, so how electromagnetic waves behave in fibers, then you can look into that chapter. So actually now I want to discuss something that's I believe which is more interesting and more relevant to you, is how actually are the electromagnetic waves produced. So remember that in chapter 9 we discussed how after we produce the electromagnetic wave, how the wave behave, but we never discussed how are these waves produced in the first place, right? So imagine that to produce a wave, we must have some sort of changing magnetic field and electrical fields. So if you have a static configuration of charge or current, then that will never produce any electromagnetic wave, right? So how about if we move the charge at a constant speed? Would you think that will produce electromagnetic waves? So say I have a positive electron that's moving at velocity v, which is a constant. Then the field it will produce will change as a function of time and position, right? But does it produce any electromagnetic wave or radiations? So any reason why or why not? So sorry. sorry, I didn't hear clearly, but I guess what you mean is that you sit in the same frame of reference, right? Okay, so say that, imagine that if you are in the frame of reference of that particle, then it's actually standing still, right? So the waves, so you won't have any waves if you are co-moving with the particle. So the only way to have changing electric magnetic field and that produce waves is to having a charge that is accelerating. So there must be some sort of change of motion. So because based on special relativity, whether the particle is moving at a constant speed or a zero speed actually doesn't make much difference. So only if they are accelerating, they are actually making some difference. So so the first point is that we have to make it accelerate. So then also, by the way, if you have a current that's also accelerating or it's alternating, then it's also fine that it will produce a changing magnetic field, and this changing magnetic field can produce changing electric field, which produces waves and in an infinite loop. So however, what I still want to mention is that remember that I claimed the magnetic field effects are weak effect comparing to electrical fields. So a changing current doesn't produce as much radiation or as much EM wave comparing to a changing charge. So if you want strong radiation, you would actually prefer some sort of changing charge instead of current. So one of the simplest radiation pattern is called ideal dipole radiation. So what I mean here by ideal dipole radiation is that consider I have two metals or two charges that's oscillating back and forth in the opposite directions. So say that for the say that there are two point charges. That's one is positive sign and is oscillating back and forward, and another is a negative sign that's oscillating back and forward. And this will be a dipole that's having an alternating sign, so which is can be expressed as p as a function of time with a dipole moment p naught times the time varying oscillation cosine omega t. Of course, it's along one of the axes because the dipole has a fixed direction. So this kind of radiation is called ideal dipole radiation. But I'll actually claim that the most familiar waves is actually produced by this kind of dipole antennas. So the Wi-Fi that you use are produced by this this kind of dipole oscillation. So even though it's not ideal, so if you take a look at one of your Wi-Fi antennas and strip it down maybe so to take off this plastic cover, and you can see that inside there are two metals. So on these two metals, that is one is a positive charge side, one is a negatively charged side, and there is actually a wire that's connecting these two metals, and there's a current, there is a voltage difference that is connecting the two different metals, and the voltage difference is AC voltage difference, and the frequency of that driving force will be exactly the same as your Wi-Fi frequency. So now this is not so perfect dipole, in the sense that here the length of this antenna is sort of one. So one of this metal is 1/4 of your Wi-Fi frequency. So for 2.5 gigahertz Wi-Fi, which is about 12 centimeters. So for one of this, for the both combined gives about 6 centimeters, and each of them gives about 3 centimeters for this metal. And this is the number is chosen such because for this kind of length, it will introduce resonance effects. So it's sort of like you are playing a guitar, and if your resonance volume is exactly on resonance with the frequency that you are playing, it will amplify the Wi-Fi signal. So besides that, you can sort of treat this as an ideal dipole radiation. So now, if you are curious of how how the Wi-Fi radiation signal behaves, you can simply turn to chapter 11 of Griffiths, and they derive in detail how the radiation behaves. So I'm not going to give you details of how exactly these radiation patterns derive, but if you follow the textbook, and you see that they make several approximations in this problem. So the approximations say that we are looking at ideal dipole. So the size of this metal object is small, and then the small compared to the wavelength, and also we are in the far field limit. So the electromagnetic radiation we are looking at is far away from this antenna. And now, if we make all these approximations, we can solve for the field. So the field, we can obtain a vector field as a function of both the radius, the angle, and the time as a function like this. So it's actually a very simple and intuitive expression. So by the way, we have to first ask one of these questions, and so would you think the Wi-Fi signals are omnidirectional, or do you think that's like would you think the Wi-Fi actually is exactly the same in the all solid angles, that no matter where you are from the Wi-Fi antenna? So here the omnidirectional, what I'm asking is that it's a solid angle instead of 360 angle. It's a 720 solid angles. So does it? Would you do you think they are the same? Like the Wi-Fi signal will be the same or not? Okay. Yes. So here, from the physics point of view, now if we check out this shape, then we know that this shape has sort of spherical has sort of the azimuthal symmetry, right? So if you put into the spherical coordinates and set this as the z-axis, then you would imagine that along the phi angles, the radiation must be exactly the same. But along the theta angles, there can be some sort of dependence, right? So, but right now we are still not sure, like whether the radiation will be more along the z-axis, say that whether it's possible that the signal here is much stronger, and it's also possible that on the sides are stronger, right? We are not sure yet, and if you don't know that, then one guess will be that because the antenna is pointing at the direction, so it's highly likely that the signal here will be strong, right? So now we can do the calculation and calculate how this how the radiation looks like. So from this vector field A field, we can obtain the corresponding electric field and the magnetic field. So the electric field is simply the time derivative of this vector potential. And now if you do this calculation, you get an expression like this, and you can also get the B field from the curl of the A field. Now look at these expressions. So one, say that we take the limit where the frequency goes to exactly 0. Then this corresponds to a constant dipole, right? So in this constant dipole, you see that both the E field and the B field is exactly 0. That means, which makes sense because for a constant dipole, it doesn't radiate. So there's no radiations, and this radiated E field has to be exactly 0. But if we increase the frequency, then this term is no longer no longer 0, and it becomes finite. And now we see that there is this dependency on radius as r. So the E field actually decrease as a function of 1 over r for the E field, and it decreased as a function of 1 over r for the B field as well. And what's different from the electromagnetic wave in the previous chapter 9 is that here you see it doesn't depend on x, y, or z, but it actually the oscillation part depends on the r. So it means that we are looking at a spherical wave instead of a plane wave. So now the next we can try to do a cross product of the E field and B field. So remember that the cross product gives you the pointing vector, which points at where the electromagnetic wave propagates, right? So now the E field is along the theta direction, and the B field is along the phi direction. So the cross product of theta and phi actually gives you the radial direction, which makes sense. So if you oscillate a dipole, then the radiation direction is radial direction. So it will radiate away from that dipole. And now if we do an average of this pointing vector, then that gives you the intensity of your Wi-Fi strength. Then this means that here so this will actually give you how your Wi-Fi signal looks like over the whole space, right? So it makes sense that the dependence is 1 over r squared, because you imagine that if you draw a circle, a spherical circle, then what you get as you radius of the circle increase must keep a constant. So as it radiates away from the dipole, the power must be a constant and doesn't decrease or increase. So what's in the angular part, there is the sine square theta, which means that now remember that we have the dipole here in the z-axis. So at the theta equals 0, it's aligned with the dipole or aligned with your Wi-Fi antenna. And at that direction, the power is actually exactly 0. So it's actually sort of counterintuitive. So say that if you don't want if you want your roommate to have zero Wi-Fi signal, you simply point your Wi-Fi antenna to your roommates, and that gets things done. But in reality, it's not exactly that case, because just like light, Wi-Fi signals can travel by reflecting off a surface, and also has it's also more wave-like, so it actually can diffract and propagate in a path that's not completely straight line. So, but in general, you will have actually reduced signal strength along the z direction. So if I try to plot how your strength, how your Wi-Fi signal looks like, it will be over the left in 3D. So what I'm plotting is here is equal strength surface. So at each of these surface points, the signal will Wi-Fi strength is exactly identical. So as you can imagine that the larger this size, then the stronger the signal it must be, at equal distance. And here you can see that there are no Wi-Fi strengths at all when you are actually exactly on top of your Wi-Fi antenna. So here on this graph, I'm simply trying to plot a cut. Say this is the axis, and this is the x-axis. So this is simply the axis over x and z. So and on the right, I'm plotting the axis as x and y. So you can see that if you place your router Wi-Fi signal, Wi-Fi antenna that's straight up, you imagine that as you go around your antenna, the Wi-Fi strength is exactly equal. So it's equal in the azimuthal direction, but not equal in the z direction, or this theta direction. Okay, we can. So we just discussed how single antenna's radiation pattern looks like, and so it's sort of a donut shaped. It's actually weakest in the direction of your antenna, but the strongest around the side. Yeah. And in this, say that if you place your antenna straight up, then on the same floor, the strength is roughly equal if you have the same distance to your antenna. So one suggestion for you when you get back home is that instead of pointing your antennas to the left, to the right, or at arbitrary angles, you should actually, the best is to place your router in the surface that is similar to human level, and point your Wi-Fi antenna straight up. But sometimes your internet port can be in a different room as where you want to put your computer. So oftentimes you actually have to put the router and your device in different rooms, right? So the strength, why the Wi-Fi strength in different rooms actually hugely depends in where you live. So in US, it's actually a lot of buildings are made of wood, and for wood, the Wi-Fi signal can pass through the wood without any decay. So you can sort of wood to Wi-Fi signals is transparent. So it's like glass to visible light. And but say that if you put the router here, and it seems that a lot of the walls are made of concrete, and instead of bricks or wood here. So for concrete, there are metals inside, and if you just like what we discussed earlier, right? So if you put any electromagnetic waves into a metal, it will be either absorbed or be reflected back. So you will have decreased Wi-Fi signal very quickly once you pass one wall. So say that if your rooms are separated by a concrete wall, then you will never have as good signal as if they are in the same room. So now another technique to increase the signal is actually to do something called beam forming. So here for beam forming, it means actually multiple antennas. So what I mean is that now imagine that you not only have one single antenna, but two. So remember that the electromagnetic fields are waves, and the equations guiding them are linear equations, right? So based on the superposition principle, you can to get the wave propagating, you can simply add up two solutions. So having two antennas, it simply means you have two sources, and you simply need to add up the waves either constructively or destructively. And so here, this is trying to plot the waves for having two antennas that's exactly separated by the wavelength over 2. And at that wavelength, in the direction, so in the y direction, so you sort of see that as you go along the y direction, it will always have destructive interference, right? So because the wave that's produced by the first antenna is exactly cancelled by the wave producing by the second antenna. And however, that's not the end of the story. If you look at from the side, it's actually always constructive interference along the x direction, because the if the two antennas are exactly in phase. So as that case, the distance along the x-axis to the two antennas are exactly the same. So having two different antennas actually enables you to engineer the shape of your power distribution. So nowadays, so if you want to say that increase the signal strength, you are not allowed to arbitrarily increase the output power of a single antenna. That is because designed by law or by restrictions from different countries, you cannot radiate too much power. Otherwise, you might interfere with your neighbors, or in some extreme cases, you are not allowed to emit certain frequencies outdoors, because some of them could even have like other uses, say military use or emergency use, and this limits the power output of a single antenna. But say that we have multiple antennas, even though we have the same output power by integrating over all space, but we can concentrate that power into the region of interest, because say that if our device is exactly locating at the point or the lobe over this place, the signal will be boosted, and it will not only boosted by a factor of 2, but by a factor of 4. Remember that the E square or the E and the B will both increase by a factor of 2, but the intensity will increase by a factor of 4, right? That's the increase of your signal strength. So if you let your source move slightly away, so this is not only lambda over 2, but multiple far away from each other, then you can even create interference patterns that are strange or have multiple small lobes over here. So instead of 2 big lobes over here, so this structure is much smaller, but it can actually be quite useful, as you can see later. But the message here is that by engineering the shape, you can increase the power, so or increase the signal strength received by the receiver. So this is actually one of the technology that's called beam forming. Now let's let's check the next is to how exactly can one increase the throughput of our Wi-Fi signal, say. So I'm not sure if you are familiar with Wi-Fi standards, but you might heard some words as Wi-Fi 6, and before the Wi-Fi 6, there are previous generations of Wi-Fi, right? So, from the Wi-Fi 4 to Wi-Fi 5, we include there are actually more frequencies added to the Wi-Fi. So previously in Wi-Fi 4, we are only allowed to use 2.4 gigabytes frequencies, or more precisely speaking, the frequency is close to 2.4 gigabytes. So if you have tried to go to your Wi-Fi router settings to set your Wi-Fi signals, you might notice that there are multiple channels of choice, like channel 1, channel 6, channel 611, and you are able to choose from all these channels. However, in our minds, in physics' mind, we are actually talking about fixed band frequency width. So we are actually talking about a set of frequency about 20 megahertz around channel 1, and a set of frequency that's around channel 6. And we can carry in certain amount of information in one channel. That is because if you because remember that for different waves, if you look at their underlying solutions, the solutions are plane wave. You can think of them as plane wave solutions, or it's actually the spherical wave solutions are exactly similar. For these solutions, different frequencies are orthogonal to each other. So in principle, you can carry different information in different frequency channels. And here in 2.4 gigabytes Wi-Fi, the width of this channel is limited, so you don't have many frequency choices in the 2.4 gigabytes Wi-Fi. But in 5G Wi-Fi, you are provided more selection of channels, which give you more throughput, or you can carry more information from it. Now, The second technique that I want to talk about is actually more relevant, or like it's from the physics point side. It actually use more physics instead of simply brute forcing. Use more channels. So here, the technique is called MIMO. So I guess you must have heard this word. So it means multiple input and multiple output. And this has been introduced from the Wi-Fi 4. So here, what I mean by multiple input and multiple output is that we have um, multiple input antennas. Remember that if we have two antennas that's radiating waves, we can using the beamforming technology, we can engineer the shape of the power of the radiation, right? But now here, what's different is that we can add multiple receivers. So imagine that we have a receiver sitting at a point over here, and another receiver sitting at so this is called receiver A, and we have a receiver B sitting at a different position but close by, right? So nowadays, if you look at your specifications for your say for your phone, typically you have at least two antennas. So this is the antenna of the receiver. And what does this? Why does this help you? So the reason is that now here this is a pattern that's being generated by the two of the transmitting antennas, right? But here you can see that only at the antenna A you are receiving a strong signal, and at antenna B you actually not receiving any signal at all. But now again we can still use the superposition principle. We can engineer the phase of these two antennas a little bit, and construct a slightly different pattern, such that B is actually receiving more signal, and A is actually receiving much less signal. So in this case, we actually are able to deliver different information to A and B differently. So you can sort of, even though the antennas are delivering at the same frequencies and at the same time, because they are positioned at slightly different positions, you can still carry information differently. So this means that actually the number of throughputs depends on the number of antennas. So that's why that in the modern days you see a lot of antennas, both in the router. You can see like 8 antennas or even more, and even in your receivers in the say for your phones, you actually have more than at least 2 antennas. So, but for the antennas in the phone, it might be hidden. So the edge here might be one antenna, and you can see that it has been cut here by some plastics, and the edge here is another different antenna. So this phone actually has at least 2, and exactly has 2 antennas. So you can use these 2 antennas to receive slightly different information. Then that's actually, so the number of throughputs actually can be determined by simply the number of the antennas and the number of the frequency channels that's being allowed. So the next is we've discussed how the Wi-Fi 3 to Wi-Fi 4 increases the throughput, and how Wi-Fi 4 to Wi-Fi 5 increases the throughput. But from the Wi-Fi 5 to Wi-Fi 6 is simply some technical improvement. That is, they increase the number of channels and the number of antennas. So from the physics side of view, there's no improvements in the basic principles, but on the technical side, you will you will experience through total increased throughput. Okay, so this pretty much summarize what I want to share with you, but I want to mention that please try not to share the homework solutions with the students that will be attending the class next year, and also want to have some outlooks. So remember that we in this in the 3041 we are always discussing classical waves. So we are treating everything. So we are treating the Maxwell's equation classically. So which means that the light intensity or the E and M fields must be reasonably strong, but remember that they cannot be too strong, because if you have too strong lights that's intact with matter, then remember that we always assume linear medium, and this if the light strength is too strong, this susceptibility is no longer a constant, and it depends on the electric field. So if you have strong light, you are in the nonlinear optics region, and here for the Maxwell equations and everything for the if you include linear medias, we are still in the linear optics regime, and also we cannot have too weak of a light. Say if the light if so nowadays we are familiar with the wave and matter duality of light, right? So the light can also be treated as photons, and now if the light has the E field are too small, then we have to treat the number of photons as countable, and we have to quantum mechanically treat the light. So this is in the field of quantum optics. So what I study is to study the interaction between the atoms and the light. So you can think of we are trying to play with the atom and the light, but here the light means the AC electric and magnetic field. So there are fast oscillating electric and magnetic fields. We can also treat the DC electric magnetic field, which is a constant magnetic field or constant electric field. So what I do is I typically treat the atoms using quantum mechanics. So we are trying to but for the light, we sometimes mostly treat this as classically, so just like what we do in the physics 3041 in this entire lectures. But sometimes we need to choose the quantum mechanically. In the case, say that if you put a light into a cavity, and then the cavity can support different modes. So, but you can put a few number of photons in the cavity, and you have to treat the light quantum mechanically in this case. So, in what I do, typically what we do is to try to slow down the motion of the light, and we can slow down the motion. Slow down the motion of the atoms using lasers. And I'm not sure if you have heard of that before. So this is called laser cooling. So instead of using laser to heat the atom up, we can actually do the reverse way, to use the light bulbs actually to slow down the motion of the atoms. So another way to slow down the atom is to engineer some magnetic potentials to trap the atoms. But in any way, we must what we want to do is to put the atoms in a motional ground state. So the in this case, so the temperature of the atoms will be dropped to almost zero temperature. So that's why it's called ultra cold atoms. So in the lab, for ultra cold atoms, it can reach the temperature of 10 to the -7 or even to 10 to the -9 Kelvin. So this is much colder than what the coldest space in the universe. Say, in the outer space, you may reach a temperature of a few Kelvin, but that's still not cold enough. So in this region of the cold temperature, for sure, we have to put that into the vacuum, right? So now, once the atoms are actually slowed down, they will behave like a wave. So then we have to use quantum mechanics to describe how the wave behaves. So finally, I want to mention that so not only we can use light to slow down the motion of atom, we sometimes can also use an atom to slow down the motion of the light. So we can even stop the motion of the light. So it's called the electromagnetically induced transparency. So imagine that it actually it's actually similar to what I just described about the resonance condition or the resonance shape of this material. So I will go back. So we just discussed the dispersion relationship. So this is the n as a function of the frequency, right? So that is if we shoot some sort of light into the matter, if it's at a resonance position, then most of the atoms will be absorbed by the material, and it will do some spontaneous emission. So now what we can do is actually to we actually can engineer some sort of three-level systems, and now we put into a media, but instead of a two-level media, and we have a three-level media, and now we can have eventually so we have one additional laser couples two of them, and if there is photon comes into this if there is photon comes into this state, then it will be absorbed, and then it will be pumped again, but it should be emitted back to the could be emitted back to the ground state. But we can engineer the system such that once the light is coming into this into the media, then it can be captured by the atom immediately because of the resonance. Now we also have but this light won't be spontaneously be emitted, but it will emit again in exactly the same. If we engineer the system such that it emits, it's not a spontaneous emission but an induced emission, then the light can be propagated to the exact same location, same direction, and now because of another atom will absorb that same light, and then store the energy, and then somewhat again emits the light in the same direction. So you can sort of think that the light, once the light wants to travel to the right, it has to be absorbed and be emitted by lots of atoms, and in this way, but the light emission, the absorption and the re-emission takes time. So we actually can think of this actually change the dispersion relationship. So instead of a normal dispersion like this, in the in the uh, in the special engineered materials, the dispersion can be reversed, and it has a large slope. So I'm not sure if you have heard of the difference between the group velocities and phase velocity. So, but for this kind of media, the group velocity is almost exactly zero. By and this zero group velocity means that the light is almost stopped and doesn't propagate at all. So this is the classical. This is a cartoon picture of how one single photon actually behaves. But to exactly calculate the group velocity, we can get it from the dispersion relationship. So so if you are interested in doing some research in ultra cold atoms, then you can try to send me an email and discuss with me. So that is all I want to say. So do you have any questions? Like, so this will be the last of the lecture. So please